end of the semester, at least, I was told like we were getting rid of it and I needed to move on. Apparently, I could still use it, which I might because I find Teams to be irritating. Oh, there we go. Okay. 54. Got it. Got it. Okay.
At least my handwriting's intelligible.
I'm sure it's great. Okay, 54. Okay, so our goal on this one is to get P. This is number 54 on your written homework, the very last problem I think that you guys had to do. Did you do it? Did you just ask me, did I do it? What? Why did you ask me that?
It's been forever. I did.
Okay. Okay. I think I copied this down right. I got a little bit lost in all the parentheses. Yep. Okay, so we're supposed to be showing that this whole thing up there is equivalent to just P. I'm not going to do this for you. I'll do this with you. So, what are your thoughts looking at this? Y'all switched seats, right?
Yeah.
Okay. Who told me to do De Morgan's Law? Okay. Do De Morgan's Law right here. Okay. So we have, if I do that, this would be P and not Q. Then leaving everything else alone. Oh, I'm supposed to explain this. There's my explanation. Okay, next. Okay. So you don't have to do the distributive law because the symbols are the same. You do the associative law, which is just going to move your parentheses around. Is this what you mean? This is what I did. This is what I'm seeing. Yes or no? Oh, this is all in parentheses still too.
Same thing, I just called it wrong.
Oh, okay.
Basically, just to eliminate the extra.
Yeah. So this is just regular old P now and not Q. And this is P and Q. Yeah, we're going to undistribute that P and. So it's going to look like P and then not Q or Q. Oh my gosh, I forgot to look up whatever I was supposed to look up. Dang it. Now while I'm looking at that, I remember I was supposed to do that. I'm really sorry. I forgot. I wasn't intentionally not doing that thing. I just forgot. How about not Q or Q? That's always true. What's that rule called? Negation and then just P. Identity. The table, yeah, has the names on them, right? Yeah.
Yeah, okay.
Okay. How do we feel about that? That's fine. You can do it different ways. Oh, yeah. Yeah. Like, if you, there are, well, did you start with the Morgan's Law? I guess beyond that, yeah, yeah. That is the only first step I see, but after that, you could do other things. Okay. So your written homework number 1 is due tonight by midnight. You can email it to me, or if you have it on paper, you can hand it to me before you leave the room today. Or give it to Julia by 5, I guess. It's an option too. You know Julia. Julia sits at the desk right up in 206. Right, she's the gatekeeper for all of us. Yeah, you know Julia. Okay, I don't remember where we are in our notes, but if I go to our notes, I'll figure it out. We are here. Okay, cool. Page 13. Oh yeah, I was supposed to look at that thing. Man. I wrote it down here, which isn't helpful because I haven't looked at this, right? I should write it down as something I'm actually going to look at. I will write it down. All right, so we are going to use truth tables to determine if the argument forms are valid. I would like to only do like one of these two, so you guys can choose which one you want. Okay.
I don't like the looks of
The first one is Modus tollens. That's a, this is valid. That's the other of the two, like, normal, the, like, common logical equivalence forms. Modus tollens, that's it. P implies Q, not Q. That all gives you P, not P, I mean. That's because the conditional is equivalent to the contrapositive. Okay. So on this one, the argument here is, the premises here are P implies Q, also Q, that those things imply P. You guys can tell me right now whether or not that's valid or not, whether or not that's valid, and what is your response? It is not valid, Marina says. Marina, do you know why? Yeah, it should not, right? The P implies Q is not equivalent, remember, to Q implies P, and that's what this is saying. So that is not a valid argument form. So let's look at that in a truth table. Our truth table, it will look like this. P implies Q and Q. So premise 1 and premise 2 implies our conclusion P. Okay, so our first two columns are normal P, Q. And then I'm going to do P implies Q. I'm going to call this 1 and this 2. I'm going to say 1 and 2. We'll call that star implies P for my conclusion. All right, so P is true, true, false, false. Q is true, false, true, false. P implies Q. True implies true is good. True implies false is bad. False implies anything is good. All right. And then we have, we're looking at the and between these two things. So we need both to be true. which happens here and there, but not in those two.
And so for the third, fourth column, what are we looking at?
We're looking at 1 and 2.
Okay.
True and true. False and false. True and true. True and false. Okay, so then we are looking at the implication from star to P. So we have true implies true, which is true. We have false implies something in those two. True implies false in that third row. So this is not a valid argument form. Okay, so in class on Tuesday, we were talking about critical rows. And remember, the critical rows are the rows where all your premises are true. So in this case, we have 2 critical rows. These are true here, and you get that from that column. But so those are your critical rows. And then you want to look at, does the truth of the conclusion follow the truth of the statements, of the premises? So we have true, true, true. Yeah, that's good, right? Because our conclusion is P. But this one we have true, true, false, and that's bad. So this would give you a false in that critical row, which is a problem for the validity of the argument anyway. Okay. So what we're going to do now on 3, 4, and 5 here is to decide which rule of this table at the top of the page that we're using. So it is below freezing now. Oops, that's not a pin. It is below freezing now. And then I've got my therefore, so that means my bar in my column has and my argument has happened. It is below freezing now. Therefore, it is below freezing or raining now. Are we okay with that? Does do the letters that I put with that make sense? For freezing and raining, I assume those make sense. I meant just the structure makes sense. I assume the letters make sense to you. Okay, so F implies F or. What form is that? Yes, it is generalization, Whitney. All right. Would somebody else like to do number 4 now that you know what we're doing? Kaylee, you're making me sweat with your coat on in this room because I feel like it's 100 degrees in here. And you're just wearing your coat like it's all cozy. Okay, it is. Kaylee, can you do number 4? Okay. Okay. What rule is that? I don't know if I wrote this down. Did I? I sort of. Yeah, this is specialization. Good. Oh, boy. Okay. I'm going to take over on this one.
Like the 2 ones. All right, here's a pair.
Right. And the letters you choose aren't going to make sense later. Because if you just jump in and start making letters, which is what I'm going to do, we're going to be confused, but it's okay. We'll figure it out. If it rains today, then we will not have a barbecue today. How do we feel about that so far? If we do not have a barbecue today, uh-oh, we will have a barbecue tomorrow. Tomorrow, let's do it. I'm working on it. I realized that it looked too bold. Do you want to use something else? Let's use an M for Spanish tomorrow. Okay. Therefore, here's my hint for my bar. If it rains today, then we will have a barbecue tomorrow. Yes. Whatever you're whispering is the right answer. It's got a lot of letters in it. That's transitivity, right? We just sort of can just sort of ignore these guys. All right. Cut off the middleman. Are we good? Any questions about that? 3, 4, or 5? No. Okay. Oh, this is my favorite thing that we're going to do today. No, it's fun, but it can get messy. So you got to be careful about how you organize yourself. And I find that the way the book does this is really confusing, but it might make more sense to you. So, well, what we're going to do basically is make a string of things that start at point A and end at point B, and we're going to combine them in the middle. Okay. It may make sense once we do it. The first one's easy. Let's just start there. It's the easiest of them, I should say. It's not just easy. So we have a premise 1 and a premise 2, and this is our conclusion. Are we following the structure of the argument here? So we can do this with a truth table, but like that's really annoying and they can get really long and gross. So we can also do this with using those rules of inference and combining our premises. So we have premise number 1 is not P. Premise number 2 is P implies Q. We're trying to lead to a place where we have just Q. Okay, so how can we like move a step closer to Q?
Because it's a negation, it's 2 negatives. Can we make that positive?
Sure. So this becomes regular old P. Yeah, these two together using what rule? P implies Q and P. That's one of your big two. This is modus ponens. So this is negation. This gives you your Q. And you're done. Okay, so obviously they get harder than that. And like before with the other one, there are different ways to do it. So you don't have to do it the way your neighbor does or the way that I do necessarily. So on this one, we're starting with not P implies Q as premise number 1. Premise number 2 is not R implies not P. Premise number 3 is not Q. Premise number 4 is R implies S, and we're trying to get to just S. Okay, so any way that you see to combine any of those two, basically we want to leave the R implies S alone, right? We want to save that till we're ready to use it so we can get to S. That's the only one that involves S. So we know that needs to go probably last, right? We need an R to happen somewhere so that we can use R implies S, right? Okay, so Charlotte's using the using the transitive property again, right? That's what you're doing. So the transitive property here says that not R actually implies Q.
We got not Q and not Q though.
I don't have a not Q and a not Q.
Q and not.
The whole thing. Heard it, so. SR.
No. Because if you negate that piece, you've
R and not Q. Like, they, like negate the not R implies Q.
so you can't negate a piece of the argument, right? Because then you're changing the whole argument. You could rewrite that implication as an or statement, right? What is the conditional equivalent to if you don't negate it? Right? It's equivalent to not P or Q.
Oh, that's what I was trying to get at. Yeah.
So not R or
Q.
Q. Yeah. Then not R or Q. This is not how I did it, but that's cool. This is fine. It'll still work. Okay.
Not
Okay.
Q.
You have R or Q and not Q. So just R. What?
Q and not.
You have this is what is that called? I didn't name it. That's unfortunate. Yeah, this is modus ponens. Okay, so I did not do this way, and I found that I personally would have gotten lost in the middle of that. So I'll show you maybe what I did. How's that sound? This works, obviously. There's nothing wrong with it, but so I would have started like Charlotte did with using the transitive property there. So this gives me not R implies Q. Well, right now, not R implies Q with a not Q gives you not R. That's modus tollens. So like modus tollens, remember, is P implies Q and not Q is the contrapositive, gives you not P. So here, looking at not R implies Q and not Q gives you not R. So that's just R. And then R with R implies S. And modus ponens gives you just S. Okay, so that's why I said you can look at your textbook and figure out how they do it. They do it with numbers. They say like 1 and 2 gives 3, and they make a new 3. And I find assigning a whole bunch of new things to be really confusing. But whatever works for you. This is the way that makes sense to me. Yeah. But the textbook will like number these and then do a thing like, well, 1 and 2 gives not R implies Q, and that's 3 or whatever. And then they'll say 3 or maybe this is 6, right? And then they'll say 3 and 6 gives, and then define a new number for that thing. I think it's messy, but also I can't do it. I think that once you like do your own, that you'll find a way that works for you to organize it. And as long as you are doing stuff in a way that I can read it, that's fine. I don't think that's that hard to follow personally, just arrows. But I'm not using actual arrows because then you'll get confused about what's a conditional arrow and what's moving to the next step arrow. But so those lines are our connectors between these things. I think it's fine. Making yourself like columns, like this is your first column, you've got this many, and then you combine them and make fewer, and you combine them and make fewer in the next column. That would work too, until you get to the conclusion. Just do it in a way that makes sense to you, especially if this doesn't. Okay. So a good way to think about this, and like we talked about this on this one, the R implies S thing, that's the only one of those premises that involved our conclusion. So we knew that we were going to save it till the end. So sometimes it is easier to start that way, to start at the conclusion and work your way backwards. And including reasons for your steps. Obviously, I didn't do that on that thing up there. Sorry. This is transient property. This is modus tollens. Okay. Any questions about that? That's the word work. I now look at that and realize it doesn't look like the word work, but that is what that says. Are we okay? Yes? We're in a good spot, feeling good? Guy, how are you doing? Okay. We don't have time to do all of these, but we can, what I will do is let you guys try and see what you can like, if you find a way that works for you. So why don't you do number 2? And I would encourage you to not talk to your neighbors and see what you can do first, because we don't all think the same way. So. Oh, you can switch the order. Are we fine with it? Or not fine with it? Fine. Fine, fine, fine. Anybody have any questions? Yeah.
No idea that I did it, but I don't know all what
Well, the names are in the table, except for the ones that don't have names. And if they don't have names, well, like I put a question mark because I also don't know what that's called. What is it called?
Is it identity?
No, that's not an identity. I don't know what it is. Well, I mean, you could say like 7 in the table. I don't know. Like, justify yourself. It's in there. I promise, Dr. Thomas. Upper right corner. I don't know. Yeah, that is the one it is, right? Yeah, it's this one, right? The one next to transitivity. I'm just kidding. I don't know. Just use something. Or say, duh. No, I'm joking. Maybe don't say that. Okay. That's not nice. If it's P or S and it's not S, it's got to be P, right? Right? Yeah. I mean, that's the whole table is called common logical equivalences. So CLE 7. I'm not going to go check. It's going to be fine. I'm going to know if it doesn't work. Okay. Do you want to try another one, or do you feel like this is a thing you can figure out with given enough time and effort, or do I need to do another one with you? Marina, I'm just talking to you. How do you feel? Do you want me to do another one, or you feel good?
Sure.
Okay. Okay, so I'm looking at this and I'm thinking, okay, what do I see that I could do from the get-go, not even considering what my conclusion is supposed to be, but the redundancy that I see in the premises is the not P implies R and R implies S, that I can get rid of those R's, right? Which is good because there are no R's in my final answer anyway, right? So that's a smart move would be to combine these two things into not P implies S with the transitive property. Now here's the issue. I need a not Q implies S. I have a not P implies S. I also have P implies Q. So I would like to, in theory, because I have my answer is still a conditional. I would like to combine these two conditionals into another conditional, right? And the way that I do that is the transitive property. That doesn't work right now as things are, right? I need a not P to be where Q is to do this, right? Right? If this was a not P, then I could combine those with a transitive property, right? Yes, Logan.
Could we do the contrapositive?
Mhm. So contrapositive says that this is equivalent to not Q implies not P. I mean, now I've got it. I have those not P's in a place where I can eliminate them, which is good. And the first thing is a not Q. The last thing is that S. And using the transitive property, that would give me, again, the not Q implies S. Okay. Cool. Okay, so we're going to take all of this stuff and sort of make it bigger. So we talked about this maybe on the first day. Is the sentence x plus y is greater than 0 a statement? And the answer was no, not yet, right? Because we don't know what x and y are, we don't know if this is a true or a false thing. You're going to have a question on your web assigned homework that's a little tricky. It says something like, he is a math major. That a statement or not? Because we don't know who he is. So we don't know if it's true or false. If we knew who he was, we would know if it was true or false. But because we don't know who he is, we are unsure. Right? So like on this one, we don't know what x and y are, so we don't know if this is true or false. Okay, so what we're building right now is where we could have a way to basically define what x and y are so that this thing could be true or false. So a predicate is a verb phrase that describes a property of objects or a relationship between objects represented by variables. We also looked at this with that example that like if x is greater than y, then x squared is greater than y squared. And then it was like root 2 is greater than this thing. It used a specific example after making a generic statement. That's what this is talking about. So for this statement, x is greater than 3. Sorry, for this thing, x is greater than 3. X is the subject, and greater than 3 is the predicate. So this is a property that x can have. We're going to do this with like basically like a function notation. So p of x. Once we have a value assigned to to x, then it becomes a statement and has a truth value. Before that, it doesn't. So in this example, our p of x, remember, is that x is greater than 3. So p of 2 means what? Okay, so the generic statement is p of x. That statement is that x is greater than 3. So p of 2 means 2 is greater than 3. And that is now has a truth value. That's truth value is false. X is greater than 3 by itself, not a statement. 2 greater than 3, that's a statement. P of 4 is the statement that 4 is greater than 3, which is true. Again, so once you assign like an input, you now have a statement. Okay, so this can happen in like for multivariable things too. So Q of xy is defined where x equals y plus 3. So Q of 1, 2 means if Q of xy is that x equals y plus 3, Q of 1, 2 means that 1 equals 2 plus 3, which is not true. Q of 4, 1 means that 4 equals 1 plus 3, which is true. Okay, some of this is going to go off the rails just a little bit, but that's okay. It's kind of a silly examples. These are silly examples, but it works. So we're going to look at this thing. We have these variables, Brooke, Chad, Diane, and Michael. And our predicate is that X loves Y. Okay, so we're going to take these words, we're going to put them into symbols. We'll obviously go backwards as well. So Brooke loves Chad, but, and not Michael. X loves Y, L of XY means that X loves Y. So how can I write this in symbols? Do y'all have any idea what I'm asking? Let's call this, the Brooke is B, Chad is a C. That first thing is Brooke loves Chad. There it is as it with its symbolic notation. The but, not Michael, so and not, Brooke does not love Michael. Okay, remember P implies Q is equivalent to P only if Q. Brooke loves Chad only if Diane loves Michael. So it's that this part implies this part. Y'all are wearing me out. The fact that no one is answering anything. Do y'all not have any idea what I'm doing? How foreign is this to you right now? Okay, you're just not talking to me at all, so I shouldn't take anything personal about it, or maybe I should take it personally, but not about the material. Oh, I wonder why you've been whispering all day. Okay, well. Whitney's excuses that she doesn't have a voice. Where are the rest of you? Ruth, you've been talking. I'm not talking to you. You have been talking. Are we okay with this? Yes. Okay. Are we gonna get back to Brooke and Chad? I thought we were gonna get really weird with it, but we aren't. That's as weird as we. Oh, we're gonna talk about everybody loving Jerry in a little bit. We'll get there. If that wasn't weird enough for you, just hold on. All right, so we have quantifiers. Quantifiers are things that you, well, it quantifies things. So the universal quantifier is this upside down A. It's this upside down A. What that means as a quantifier is that it is for all, for every, for each. So like for all X, X is greater than 2. The existential quantifier is a backwards E. This is a there exists. For some, or for at least one. Or there is, that's a good one too. Now don't get this confused with this guy. That's the element of E. I'm about to write down all of those symbols next to one another, so. Now, what helps me is reading them as they are, so that it like trains my brain to remember. So for the universal quantifier is what we're talking about first. So for all X that are elements in the domain, so that's where the little E is, right? So for all X that are contained in our domain, that's the D. P of X. This is just the elements in the domain, like I just said. So P of X for all values of X in the domain. This is a generic thing, so we don't have any domain yet. So therefore, we don't have any X's yet. Okay, so P of X for all values of X in the domain. Let's just talk about this example and we'll come back to those blanks. So we have the predicate here, S of X. X grew up in South Carolina. Our domain is the people in this room. Okay? Yeah. these symbols mean the following. All students here grew up in South Carolina. So this is a false statement. I shall tell you that now. How do I know that this is a false statement? All right, we're going to use Marina. Because I knew for certain Marina did not grow up in South Carolina. This is false. Marina grew up in Croatia. So help me fill in that blank. It's false when is Marina the only example I needed to say that this was false? Right, yeah. When P of X is false for at least one X. And it's true when that doesn't happen. So if it's not false for at least one X in the domain, then it would be true for all of them, right? Which makes sense. You're saying for all X, this thing is true. Well, that's only true if it's actually true for all X, right? Logan, where did you grow up? Where? What part of New York?
Upstate,
So not the concrete jungle. Okay. Let's look at the next one. We have this other predicate here, D of X. X is a dog. The predicate here is that X has pointed ears. So will somebody read for me in words what this says?
All dogs have them?
It sure is, but all dogs have pointed ears. Why is this one false?
my dog is not.
Your name is Daniel, right? What's your dog's name, Daniel?
Chloe.
Daniel's dog, Chloe, does not. So, Marina and Chloe are our examples of what is called a counterexample. So a counterexample is a specific example that makes a for all statement false. To disprove somebody saying, well, all blah, 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 you would say, how about this one, right? You only need this one, and that thing is a counterexample, right? Every meal in the cap is gross. Wait, what about chicken nuggets on Fridays? That's delicious, right? So you have a counterexample, so somebody can't say that all meals in the cap are gross. Good? You think the chicken nuggets are gross? Well, that's okay. The salad's good.
I don't like salad.
Cereal. Everybody loves cereal. Charlotte, I should have known that you don't like cereal. Okay. So the opposite of a for all statement is a there exists statement. So this is really, who doesn't like the chicken nuggets? That's
Me.
they're just chicken nuggets. There's nothing wrong with them.
Yeah.
So for that backwards, you remember is that there exists. So there exists an X in the domain where P of X is true.
What are you, like, little E behind
Uh-huh. Yeah, that's the little there element of. Yeah, there's an X sitting inside the domain. It's an element of the domain. We're gonna get to set theory, but not yet, and we'll use that a lot. Set theory stuff. Like, I don't know, truth is an element of the set of all students in here. You know what I mean? That's how this works. This is how sets work. All right. So I just said that there exists an X and D where P of X is true. So it's true when there exists an X and D where P of X is true, right? So when it's true for at least one X in the domain. Okay. And how would you prove to me that there does not exist a meal in the calf that is good? If my statement is that there exists one, correct, that it's false for every single meal that the calf serves. All right. So we have the predicate here, S of X, again, is that X grew up in South Carolina, but now we're doing a there exists statement. So this is that there exists a student in here who grew up in South Carolina. Is this true or not true? Okay, Daniel says it's true. I assume because you grew up here. Now, how would we know if this was not true? Yeah, if we went around the room and said no, 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 and got a no from everybody about growing up in South Carolina. Okay. Now we have the predicate again that the dog X is a dog that has pointed ears. So what is this in symbols? I mean, in words, is that there exists a dog with pointed ears. Okay, so this is true. What's that dog's name? Huh?
That's
Okay, so I want to talk to you about something. Do you notice anything here when we were saying that these for all statements were false? Our counterexample was a there exists statement, right? To prove a for all statement is wrong or is false, you need to give an example. You need to show there exists something where it's not true, right? To disprove a there exists statement, we would need to prove a for all statement. Tracking what's happening here? If I say there exists in this room a student who grew up in South Carolina, to disprove that, I have to prove it for all that we did not, right? Yeah, yeah. and students always say, like, especially in like lower level math classes, like, is it always true that blah 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 blah? And you know how, have you ever seen how uncomfortable a math teacher gets when somebody asks that? Like, no, you can't say for certain because I can't test every single, in this, my answer is often in this class. Yes. Because, you don't want to make a claim that big that you can't actually justify or prove, right? So, yeah. Making for all statements is a big deal. Okay, so, oh, this is weird. Okay, if, and this will happen on your test, you'll have something like on your homework. I mean, you'll have something like this, for all X. Remember that upside down A is if for all, H of X implies P. You would need to define everything here. You need to define P. You need to give the domain of X and what H is. But obviously H. Okay. Oh, this is fun. Okay, so this question here is fun. We want to know if these two statements are quantified. So if a number is an integer, then it is a rational number. This is a conditional statement, yeah? Is it a quantified statement? Do you see the words for all or there exists? Can you think of a way to restate that thing? If a number is an integer, then it is a rational number. And if we want to say it like we were, for all X that are integers, X is a rational number. Ooh, do y'all know any of those symbols I just wrote down? Because it was a lot of them. No, we do not. This is element, this is the set of integers. And this is your rational.
How do you even make that symbol?
Well, it's a bolded Z. People do it differently. I don't know. That's what we were actually just talking about before I walked down here, is that as teachers, well, not gang signs, but that we could just mess up a whole generation of people. Like, I could just make you all think that, like, I don't know, that the rationals aren't actually Q, or that you pronounce this thing, which is a Greek letter, that you pronounce it mu. You don't. It's mu. But, like, I could just really mess you up because you're just putting your trust in me. And that's right. Well, and here's the thing that I said is that all of the kids who have gone through Dr. Probin's whole calculus sequence, they don't know how to pronounce any mathematicians' names, right? They're gonna move to grad school or whatever and say like Riemann sum the way that he does, and people are gonna be like, what? Because it's gonna be like a person without a British accent saying whatever it is with a British accent,
Isn't Riemann?
It is not. It's a Riemann sum. Yeah. Do you say Riemann? Because you had Dr. Probin. And if you walked into a graduate classroom in math and you were like a Riemann sum, people would be like, this American girl is calling this a Riemann sum.
Who's your professor?
Anyway, but you're right. I could really screw y'all up, but I'm not. I'm being honest with you. Oh, I didn't write this as a thing. My bad. Hold up. To actually fit the predicate subject thing, you would do it like this. That Q is that Q means X is a rational number. So this would actually fit the thing that we did. Sorry, my bad. For all X in D.
You're already doing it. You're already
Yeah. Sorry. So the like blackboard bolded letters, they're like that because I can't write in bold, and that's how it used to be on a chalkboard. Make it bold however you feel like it. But if you are not crossing your Z's, you're doing it wrong. Okay. When you're writing a Z in a math class, it needs to be different than a 2. Okay. All right. Good. All right. Y'all are going to say like 2, you're going to get to a point here. You're like 2 is an element of Z. What? Like what? I don't, make them look different. I didn't start crossing my Z's or putting loops on my T's till I became a mathematician. And I got confused about what was a T and what was a plus sign.
Yup.
And T's and Z's. No, 2's and C's, not T's and Z's. Those look different, just as they are. But anyway.
Have trouble with X's and multiplying.
Yes, I don't write X's to multiply because of that. But you also probably have trouble with X's because of Probin drawing X's like this. What is that?
He did that, yes.
I had a professor that I was the TA for in grad school that he would teach in these like long lecture halls, right? They were long, skinny rooms. Like I have no idea. The person in the back of the room was like 100 yards from the board. And he would write on the board, on a whiteboard, 100 yards away from students, right? And he would write at the very bottom. He was like on his knees writing like down here. And he wrote like this small, right? It was differential equations, so there was like a lot of symbols. And he did all of his X's like this, but there were also parentheses around. There was like, and I often sat there thinking, I don't know what of those things is an X and what is not. And I have to go teach these students in a drill tomorrow. It was, I don't know how they passed that class. Me, maybe. I don't know. I was taking too much credit for me, but like, how could they even see the board? Much less read it if they could. And that's what they all said. Like, well, it doesn't matter if I can see it or not because I have no idea what he's writing. Yeah. Y'all are really lucky. I know all of the math professors and I know we all do different stuff and we're all really different, but you're lucky. Because there are some not great ones out there in the world just floating around. He was also an alcoholic and that semester was very
This story just even better.
things really came to a head that semester. I think he's a recovering alcoholic now, but it got real bad enough that he was out the semester after that, I think.
Sounds like a fever dream or something.
Yeah.
He was in a math class and I couldn't see what he's writing. He was a really long room. He was an alcoholic.
Also, he was an alcoholic. Grad school is a lot like a fever dream. Any of you planning to go? Feels that way. Okay, the number 24 can be written as a sum of 2 even integers. This also does not look like a quantified statement, but it is. How can you write that in a way that it reads as there exists or for all? The number 24 can be written as a sum of 2 even integers.
There's a number that can be written as.
Nope, the number is 24, so. But there exists what? Yeah, so there exists 2, right? There exists x, y, and z. What do you want to call this one? I don't know. Or that x plus y is 24, right? So there exist these numbers x and y that are integers. Oh, even integers. My bad. We're gonna call this 2z. Put those right next to each other and don't differentiate between them.
Is that a fancy Z?
It's a blackboard bold z, yeah, for integers. The 2 in front of it makes it all the even ones. You know, we're gonna get into this later. Don't get bogged down in this symbolic notation yet. I'm just writing it that way because I don't want to write it all out. This is an example of what is called implicit quantification because it's implicitly there, but it's not explicitly there. Mathematicians aren't in general very creative in naming of things. So this is implicit quantification. It is a quantified statement. However, it doesn't read like one. Great. Okay. So we hinted at this a little while ago. that negating the quantifiers is, in my opinion, similar to De Morgan's law. Whoa, that M has a lot of humps. It's fine. Ugh. Actually,
It's gonna be a new symbol.
hopefully won't give you any more new symbols today. Okay, so it is similar to De Morgan's law in that you sort of like distribute the negation. So if you, and flip the sign. So you're going to flip the quantifier. So instead of when we distribute this, right, it's going to flip this quantifier and make it a there exists. And then you're going to negate the predicate. So there exists an X where this thing is not true. And we sort of did this a minute ago, right? How do we prove that that we didn't all grow up in South Carolina? Well, that there exists one of us, Marina, who did not grow up in South Carolina. Okay, let's do this as an example. So if my statement is that all mathematicians wear glasses, what is the negation of that statement? Yeah. There exists at least one mathematician that does not. So we teach this in Math 105. I'm not trying to insult you. We do it in much babier level than this, but I help them with this. And I don't know if this is helpful because I always forget how to set up the box. So I'm whatever. But this is the thing that a student taught me. And I was like, oh, okay, that actually might be helpful for some people. All do, all don't. Some do, some don't. So negations go diagonally. So negating that all mathematicians wear glasses would be that some mathematicians don't wear glasses. Yeah? That makes sense? No mathematicians wear glasses would be that some do wear glasses. The negation. Okay, and then similarly for the existential one, to negate that, the negation of the there exists, it becomes a for all statement and then not P of X. So the example I have written down is that there is a triangle T where the sum of angles is 200 degrees. So that like thinking about this is just putting the not in there, right? It was like there does not exist a triangle where the sum of angles is 200 degrees, right? Or for all triangles, it's not 200. We're in the there is, that's a sum do. This one triangle T has a sum of angles which is 200. So the negation of that would be that all triangles do not have the sum of angles being 200 degrees. Yeah? No? Okay, so distributing the negation flips the quantifier. Think about that like the De Morgan's law, right? When it is on a if it's an and statement, it becomes an or statement when you distribute the negation. Okay. So we have this statement. Now we're going to put this into symbols, and then we're going to negate it after we have it in symbols. So all dogs have fleas. The domain is our dogs. The predicate, let's call it F of D. For the D, the dog has fleas. And in symbols, this looks like for all D and D, so for all dogs and all the dogs, that dog has fleas. So I want to negate that statement. What would that look like in symbols? Okay, and then somebody else put that in words for me. Yeah, or there exists a dog without fleas, right? Okay. We have time for one more, maybe? Do we? How about, since I won't see you till Tuesday, and that's a long time from now, and we're a little bit behind because we had that day we didn't get to have class the first day of class, how about you guys see if you can do those two before Tuesday, not before tonight because you have other homework to do tonight. That sounds good. You can do that, right? Alrighty. I will see you on Tuesday. Turn in your homework tonight. If you have not emailed that to me already. If you think you've emailed it to me already, I only have Ruth's so far. Or Charlotte, you may hand it to me. Thank you. Thank you. Come on, y'all. Find a stapler. Oh my gosh. At least the two of you put your name on. Okay, all three of you put your name on every page. That's fine. Wow, can I borrow that little stapler? Don't put that away. I need it.
I have a little tiny stapler of only.
No, it's y'all's responsibility, not mine. I was going to give you Charlotte's homework instead of your stapler back. That's not right. Yes, ma'am. Yes.
So I did a little bit different, and I wanted to see if that like is okay, like if that works. I don't know, cause here I put like the double negation, and then I put the Morgan's law.
Is she usually doing it online? She doing it online?
Cyber defense?
Yeah.
No, it's in person.
So you actually did De Morgan's Law here.
Yeah, but okay.
You
So-
did De Morgan's Law here. I don't know what you did here.
Everybody besides one person, like.
Oh, here I just,
Kahoot.
oh,
How y'all playing Kahoot?
Quizlet Live.
I don't know what I did there. So basically I can just do this with the Morgan's law, and then,
Yeah, so skip this step. And I think use this and rearrange it. Yeah.
They use a living document.
I just broke this.
Of every class's So
Is
no
your
one can
stapler?
use it.
Oh my gosh! No.
So,
try and get to the library
I see why they do it. There's always
Thank
stuff
you.
that goes on, but
Well, y'all can just depend on, everybody can buy Logan staples for his stapler.
Sir Logan.
$1
Yes.
The thing I use
I
to
can
take
get-
notes, like to delete them halfway through my note taking.
So we finished it, and then my page went delete. So.
Her class is clear up until her class.
What?
The classroom.
Free up until that class?
Yeah,